Hello and welcome everyone to another SETI Live. I am your host, Beth Johnson, social media coordinator for the SETI Institute. And with me today is Dr. Peter Jenniskens, who is a senior research scientist and meteor shower expert, and my former mentor from my internship. Welcome, Peter. And also with us is Siddha Ganju, who is a computer scientist and works on machine learning for a very important project here at the SETI Institute called CAMS, which is the Cameras for Allsky Meteor Surveillance Network. And it has 24/7 coverage of the night sky all over the world, except for one place, and we'll get to that. And what it does is it looks for meteor showers and meteors. And when I was doing it, it was all very, very manual, very pick and choose which things were meteors. But Siddha came along with the FDL group and has added some machine learning into the process. And now much of it runs pretty unassisted. So it's a great little piece of technology, and we're going to talk about it today. So welcome, Peter. Welcome, Siddha. Siddha, you're muted. Make sure you unmute yourself over there. Okay.
Thank you so much.
Yeah, you're good. You're welcome. I'm really excited to have you guys here. So Peter, why don't you give us your elevator pitch on the CAMS project and tell everybody what it's really about.
So I started my interest in meteors like any amateur hobbyist, laying on a reclining lawn chair, looking at the sky, piece of paper in hand, and plotting meteor tracks in the hope of finding new meteor showers and trying to figure out, what meteor showers were active in the sky. And after years of doing that, it became clear that this was not the way to go. Because it was very difficult to actually, prove that a particular meteor shower existed that was seen visually. But then a new technology came along, video cameras that were sensitive enough to film the night sky. And that really revolutionized this field. And so in a couple of years ago, we basically scaled up the use of these video cameras. So you, instead of using just one or two, you could use 100. And that way, we are now monitoring the night sky. We have these boxes with video security cameras set up that image the stars in the sky. And the stars are being used as sort of the background that tells you what directions you're looking at. And then when we see a shooting star, it's recorded, it's tracked, and the tracking information is sent to the SETI Institute, and I have a dedicated server that takes all that data and then combines it, triangulates it. And so if we see a meteor from two sides, and we can view it this way, then we can get the trajectory determined and the direction from which the meteors are moving. And that's what CAMS is. It's a triangulation of meteors done on a big scale. So you can actually see what is coming into our Earth's atmosphere.
So Peter, I understand that you have a personal interest in meteor showers. How did you convince other people that this was an important piece of research to do?
Well, if you're in space and you have, a satellite out there, or you're traveling to Mars, meteoroids are a problem. They travel at incredible speeds and they can hit you. And you need some protection for that. And you need some avoidance for that if you can. And so since certainly around the time of the Leonid storm some years ago, there was, significant interest in making sure that our satellite park stays safe. And that was a big driver. And then later we realized that meteor showers are also tell you the trajectory, the path of a potentially dangerous comet that hasn't been discovered yet. So meteors are also a way to have situational awareness. So you can actually know that somewhere along the path of the meteoroids is a potentially dangerous comet that might one day impact us. And the meteors may be a way to warn us about them and maybe even help find the comet earlier.
Okay. I want to ask you some more about that in just a second. Right now, I want to welcome some viewers in. We have viewers watching live on Twitter, Facebook, Twitch, and YouTube. And they're viewing from right now. We have Denmark, Michigan, Montreal, Alabama, New Zealand, and Spain. So once again, a very global audience, which is appropriate.
Nice, welcome.
So welcome to everybody. Thank you for joining us today. And please continue to let us know where you are watching from. So Siddha, I promise I will get to you, but I still want to get some more background on what the research really is here. So Peter, one of the things you mentioned was not knowing where some of these comets are. How do you use the data from CAMS to trace back to what we call the parent bodies?
So the most meteor showers are caused by comets. So they when the comets come into the inner solar system, they let go of dust particles. Initially, that's just a cloud of dust around the comet called a dust coma, travels along with the comet. But when some particles, as soon as they are released from the comet, every particle has its own orbit. And so when some particles come back, they come back on shorter orbits, and other particles make a slightly wider orbit, and it takes a lot longer to come back. And so what's initially a cloud, after one orbit already becomes a stream. And it's like a river, a river of dust particles that are streaming by the Earth. But it's not staying put. The planets hustle on it, and they move the streams in and out of Earth's path. And that means that the meteors you see, when the shooting stars, when one of these dust particles enters the Earth's atmosphere and creates a streak of light in the sky, those meteor showers can be irregular. So some showers you can see in one year and not in others, because of all this, gravitational hustling going around. Jupiter goes around 12 years, Saturn goes around 30 years. So there's sort of a pattern of every 60 years things repeating. But it also means that some showers we only see once or twice every 60 years. And so, that calls for some sort of monitoring. And in the old days, that was done by visual observers, people on reclining lawn chairs. They would look up at the sky. There's many records of that, people seeing at night stars fell like rain. But that's not that's not quite giving us the information we need. The video cameras give us a very precise direction from which things are coming, and they sort of track the path of these little dust particles for a brief second. That's enough to trace its motion, its direction of motion and speed. And you can use that to then calculate what the orbit was in space. And that orbit you can compare with, the orbits of comets that were discovered in the past, to see if, you can identify one of those objects that might have caused the stream. And at the moment, we still have many streams that have no known parent bodies.
Which is a little frightening of a thought. I know you found a few. When we were doing this together, as I said before, I had to manually basically go through the data that was collected and say, this is a meteor, this is not a meteor, which was essentially like, this is a plane, clearly a plane. But Siddha, you came in during one of the Frontier Development Lab sessions, and you have done some amazing work on machine learning to automate this process so that someone like me no longer has to sit there and manually pick out what are the meteors and what are not. How did your involvement come about? What started that? Did you just apply to FDL and end up in this one, or did you have an interest? Did you, how did that work?
Yeah, so I think my interaction with FDL and the SETI Institute and the CAMS project started out with just an email from the FDL team saying, would I be interested in, this really cool project that is looking up towards the sky and finding meteors? And I was like, this is a dream come true. And so, the minute I got the email, I was like, yes, sign me up. And over the duration of the introduction of the project, I talked to Peter, I learned what the process of really detecting and finding meteors and then understanding what this meteor shower is. And that process seemed to be something that, AI could potentially be really good at, because in the past we've seen that, some of the more newer techniques in AI, they're really good at certain visual tasks. And as Peter described the process, and even you described the process, you look at something, you say it's a plane, or you look at something, you say it's a meteor, right? So of course we have the visual aspect of it that AI is pretty good at. And at the same time, you have certain statistical aspects, like how do you confirm that two tracks seen by maybe two different cameras are actually the same meteor? So we know that these things, are things or tasks that AI is really good at. So it was, just a matter of applying certain AI techniques to this data that, Peter and you had already hand labeled for us. But at the same time, when we look at the data, there's an enormous amount of data that CAMS has collected since its inception in 2010, right? I believe around 500 detections we get from every single camera. And so when you count, number of cameras, number of sites, I think there are 16 cameras per site. So that's 500 into, let's say, 600 or 500 cameras in total, right? Times the number of 16 cameras per site, multiplied by 10 years, multiplied by 365 days a year. So that's a lot of data. Now, I don't think we really want people to be sitting and looking at all this data, because it's just a lot of work. It's a lot of manual work. And so that's where we really looked at trying to replicate the scientists' thinking process and see, can we build something that really understands what a meteor looks like? And that's really how the machine learning pipeline, along with obviously the data automation, that meant, loading the data from the camera site onto the server that we have at the SETI Institute. So both of those really worked hand in hand to develop an automated pipeline. But of course, that wasn't really the end. That was just the beginning, because, ultimately we have to serve all this data. And so what I really liked about CAMS, and this is back in 2017, and I truly believe this was really revolutionary, is that CAMS had a path to deploy its AI pipeline, which, as we see, it wasn't really mainstream back in 2017. And so path to deployment really means that, maybe I make a change in the AI model, maybe I tweak the processing script a little bit today. Tomorrow I can see what its impact is based on the night's worth of data that was collected. And so that path to AI deployment really accelerated our impact. It meant, we could experiment at a much, much larger scale than ever before. And as a result, we could understand the data in much greater detail. And of course, as you're seeing behind me in my virtual background, this is one of the versions of the tool that we've developed that allows, anybody with internet access to actually go on the web and see the detections of meteors made from the very previous night. And so I think this is a really cool way of communicating science and, just seeing the impact that AI is having on a very close and a very, regular basis. So yeah, that's a bit of my FDL and CAMS journey.
Okay, well, I want to talk to you about the tool that you're showing in your background. But first, I'm going to take a second, another timeout, to welcome people to the stream. So we have more viewers: Florida, Germany, Ohio, Texas, New York, Oregon, Chicago, Pennsylvania, Sweden, Indiana, Toronto, Canada, Arkansas, and England. Again, just expanding across the country and around the world. And also, I would like to thank Sabine for her donation. Thank you so much. As a quick reminder, we are a nonprofit, so your donations do help us keep up these outreach and education programs. Feel free to drop some stars on Facebook, or super chats on YouTube, or subs on Twitch. We really appreciate all of them. Now, Siddha, you worked and developed this tool that you're showing behind you. And Peter, you mentioned before we went on air that, speaking of this whole, we can analyze data very quickly, you have found another an outburst, a very brief meteor shower. So Siddha, can you share your screen so we can take a look at that? So Peter, can you tell us what we're looking at?
Yeah, so this website is is publicly accessible. You can go there, and it's all interactive. You can actually use your cursor to move it around. What you're looking at is the night sky. People who are familiar with constellations will recognize Capricorn there, Sagittarius, Aquila on the top. So those constellations give you the directions from which we see meteors come towards us. And then each point in the map is the direction of approach of one of these meteors. And some of them are color-coded with speed, blue being the very slow ones, green in the middle, yellow and orange and red at the top. There is a number of showers every night. So you see there's a bunch of meteors that are white. Those are the sporadic, sort of the background. But then there are blobs everywhere. You see there is a dark green one. You can hover your mouse around it and you can see what the name of that particular shower is. So those are called Southern Muse Sagittarius. And you can see some details on the direction from which the meteors are coming towards and how fast they are moving. Many of these, this area you're looking at here is the direction towards the Earth is moving. So all the meteors that are coming from that direction are very fast because they have sort of these, these head-on collisions. And while the meteors that are sort of more sideways are coming in slower. And so that's why their colors are more bluish. And the new shower is that thing that sits also at the center there called Sagittarius, but it turns out to be not the Alpha Sagittarius that it's labeled with. It turns out to be a shower that wasn't cataloged until now, and it's just been named the June Theta 2 Sagittarius. Theta 2 is a star in Sagittarius, and that the direction from which they're coming happens to be nearest to that star, and that's why it's called that way. And so what's cool about it is that if you go to a date, 2 days earlier, you will see it's not there. So that you can do with.
I think it's just taking a minute to
Yeah,
load.
it takes a little to upload. So this was on June 10. June 8 is coming. So it's there. It's absent. So it's really it was there on June 10, June 11, June 12, June 13, and by the 14th it was fading and gone. And this particular shower we also saw last year in 2020, but it went unnoticed because there is another meteor shower that it was labeled with that's nearby, and we thought that it was just a regular occurrence, but it's not. This shower showed up this year, showed up last year, but was not detected between 2011 and 2018. So it's one of those streams that are very narrow and where the planets move the whole cloud of dust periodically in the Earth's path. And that's when we get to see it.
So I know we're sharing the link to this website out so that people can go and play on it all that they want to and see their own showers. One of the reasons that we're here today.
Just keep the site up there for a second.
Okay.
Because I wanted to point out to people how you can use this site. It's actually a very cool site, not just for meteor meteor scientists. It's also very cool if you're a meteor observer yourself. So if you go out at night and you plan to go out meteor observing, it's summer night or tonight, you can check on this website what showers there are active in the sky, and you can check out and see from what directions these showers are coming to us. And if you see a meteor in the sky moving from one star to another, then the way to find to which shower it belongs is to sort of trace its path back, because like all the meteors that are coming from the dark blue blob that you see there, the Southern Muse Sagittarius, I believe it was called, all the meteors that are coming from that direction will sort of show like a radiant pattern on the sky. So the meteors will shoot away from that position in the sky. And
right. So
that's
you'll see a star where they're coming from, and then they'll seem to be coming out from around it like that.
Yes,
So
exactly. Yeah.
that's how we trace that. That's why they're all named after basically that star that they're coming out closest to. I remember when I was doing mine and I found a meteor shower, and we were very excited that I found a new meteor shower that got published right as I found it. But my friends kept asking, like, do you get to name it? And I said, well, no.
Sadly, no.
No,
you get to argue about the name and so on.
Yeah.
There's many possibilities for any given name, but sadly the name is sort of anonymous in the sense that it's really the star from which things are coming towards you. That's what it's named after, and you can see that in the picture behind me. There is that was taken during the Leonid shower in 1998. And you see that all the meteors in this chart are sort of radiating away from the constellation of Leo in this case.
Mm-hmm. And so like the biggest, most well-known showers are named for their constellation in general, because they were the biggest ones. That's what we knew. But then we kept finding all these smaller ones. And so now you have these very specific names like Southern Mu, Sagittarius, and June, exactly. You start adding in like when the time of year is and all of that.
Yeah, so we've come really to the point where there is now so many showers found that sometimes a constellation doesn't have enough bias stars to name the constellation after. And so we've even in some cases gone to naming them after Flamsteed number stars, which I hate because, putting numbers in meteor shower names is just confusing. But we now have a shower called the 15 Boötids after the star 15 Boötis. And so, it's what it is. But it's very cool because, in my early days when I was out there in the field looking at the meteors in the sky, we didn't know all this. This is new to actually see the sky this way, to be able to tell where all the blobs are and all the meteor showers are coming from. And so it's cool to see that on any given night in the year, there is a handful of meteor showers that can clearly be recognized. And so if you know where those positions are, you can actually recognize to what meteor shower each little dust particle belongs. And you get to see little bits of pieces from Comet Swift-Tuttle and from Comet Neat and from this object and that object go in the sky. And they all look different. Some showers are very rich in faint meteors, like the Mu Sagittarius, I believe, are very rich in small particles. While other showers are, rich in bright meteors and show lots of flares, and some showers show no flares at all. And so you can, it's very interesting to see all the, these differences in nature's natural firework displays. So there are two interesting meteor showers in Cygnus. So those you should be able to recognize as a visual observer. If you see this, you should go out at night and try and see if you can see those two yellow showers, and can see if you can actually find the distinction between the June Epsilon Cygnets and what's the other one called? The June Rho
Cygnets.
Yeah, so there's two comets there, probably long-period comets that created these debris streams. And, at a time in June, around June 13, we get to cross through those streams and get to know that they exist and that there is this comet out there.
So one of the reasons that we have you here today is while you have all of these cameras all over the world detecting meteors 24/7, as or during the nights at least, there's a gap in the coverage, and there's a particular area that is not actually being caught on camera, so you're missing some data. Peter, will you tell us about that particular issue right now?
Yes. So in 2019, we were very fortunate to be able to expand significantly on the southern hemisphere. There was an interest in finding certain southern hemisphere showers, and we set out to do that. And we set up new networks in New Zealand, in Australia, in Chile, in Namibia. We have a small network in South Africa and our cameras in Brazil. So it's on the southern hemisphere, we're now very nicely covered. And that then dawned on me that we really ought to have a similar good coverage in the northern hemisphere, because these meteor showers that wander in the Earth's path occasionally. This one, the one we just saw, was active for several days, and so it could be seen from several continents. But in other times, these meteor showers only last an hour or so, or even less, half an hour. And if you have a shower that's that brief and you want to detect it, you want to know that there is a comet out there that's causing it, then you need to have eyes on all in the sky all the time, and that means it has to be dark, it has to be clear, and that means that you really want to have cameras at all longitudes on both the northern and the southern hemisphere.
So that leads us to another quick break to welcome some more viewers. We have people watching from Puerto Rico, Portugal, Norway, and kind of segueing into what we're talking about here, we have some viewers from India now. So the reason that we've kind of started this, we're trying to crowdfund an observatory to close this gap that you're talking about, where you're missing some coverage. And what we'd like to do is build a student-run observatory, meteor shower observatory in India. And so we're crowdfunding to put that together. Siddha, what's your involvement in that part of the project?
Yeah, so thank you for bringing that up, Beth and Peter. So we're trying to establish a student-run network in India. And so we found these 3 universities, IISER, IIT Madras, and VIT Vellore, where students are really interested in participating from not only a machine learning perspective, so understanding the models and the data processing pipelines that CAMS builds, but also from the astronomy perspective, that understanding what is the data that is being collected by CAMS and how can we take it further. So we have student-led teams from all these 3 universities in India, and they've really formed a cohesive group and are really leading the charge in establishing these meteor observatory, these CAMS stations in their respective universities. And this year we've had a student, Shayadri from IISER, actually working on the CAMS pipeline itself. So he actually helped build all the constellations that you see onto this globe. So the students have already started working, and the next step really is to raise as much funding as possible so we can get as many cameras looking up into the sky and gathering as many detections of meteors and other objects in the night sky.
Fabulous. So Peter, what are your hopes for this part of the project?
I really think this is coming together. There is the local enthusiasm and interest. So I'm hoping that we can raise enough funds to have, ultimately, with the support from India, to ultimately have a complete observatory. It takes money to buy the cameras, the enclosures, the computers, the PCs to run all the cameras. But if we have a complete network, then basically you'll get the results that you can see from other networks in the world. And that means that potentially we have a whole cover there. I think that it also helps other people in India and in Southeast Asia get an interest in this project itself, because you don't need necessarily to have a big observatory. You can participate in CAMS with single camera, 2 cameras. It doesn't add a lot of meteors. You'll be happy to, with 1 camera, you can maybe add let's say 10 points or 5 points to the map. That doesn't create a full map of the meteor activity. But if you have enough of people doing that, then you also create an observatory. And these distributed networks we now have in the Benelux, in the Netherlands, and there's also a big network being assembled in Brazil to just bring enough people together, have enough cameras overlap, and very gradually you'll find that you also start collecting a lot of meteors. And so we're hoping that the activity in India will just get that part of the world enthused and think that, hey, this is something that we can do. It's real astronomy you can do from a city, which is very rare. You can actually set these cameras up in a light polluted area. They still collect data. They still get your trajectories. So it's something you can do from home. It's, you have to make the investment to buy a computer and to buy the camera and run it and so on. But a lot of amateurs buy telescopes, and we're thinking that this is really something that can take off much more already than it does. So meteor video observing is very popular in Europe. In the US, we worked very hard to have a lot of different groups involved, and we have a nice coverage on the Southern Hemisphere. There's also a network in the United Arab Emirates, and that's so far it. So we need, and there's a network in Japan as well that is active for a long time. But that's it. And so we need to really have more people on the Northern Hemisphere take part in this, set up networks, monitor the sky, and then hopefully over time that will create really more detailed maps, see more fainter showers, and especially see these irregular showers that just show up once in a while.
So Siddha, you said that you were getting some help from some of the universities. Are there any particular students that are giving you a hand that you want to say thank you to, let people know that these are real people behind the scenes? It's not just a box of cameras.
Yes, absolutely. So from IIT Madras, we have Vaibhavi Gavas, who is really leading, forming the team, making sure that they're, getting all the inventory done for the hardware. And similarly, from VIT Vellore, we have Akhil Saxena. And from IISER, we have Swastik Shinde. And, all three of them also have their own experiences from CAMS that I believe the SETI team has also put out. So highly encourage everybody to also take a look at that and just hear from these students themselves how CAMS has impacted them and what are they really getting out of this process. So, just to drive Beth's point across, that it's not just a camera at the end of the day, it is an actual person and an actual, citizen science approach that we're really looking forward in the bigger scale of things.
Peter, when I was doing this, we had basically 3 stations and a handful of individual cameras. Yes. And it's wild to see how far reaching it is now.
Yes.
Did you ever imagine that CAMS would become this big a network?
Yes, imagine, but not really, think it might be possible. But I think that the automation that happened in 2017, that's really what made this expansion possible, because our whole effort has changed from, worrying about doing these triangulations and getting results out of all this data to just keeping the network going and having the cameras operate every night and collect data, because it's now so much easier. It's so much easier.
So much easier than driving to the observatories and grabbing hard drives and coming back to the office.
Those were the times. But you can compare that with laying in a reclining lawn chair with a piece of paper in your hands. In that sense, it's come a long way, and it's very cool that it's the future, because more and more people have cameras, and this is how we can monitor things, and it's Siddha, maybe you can bring up the website again and just click on one of these meteor shower points, because that's another real cool thing about this site, is that it's not just showing you the direction from which the meteors are coming to the Earth. It also actually shows the meteoroids in space, the orbits that we calculated from tracking it just a second or so going through the Earth's atmosphere.
So I'm just going to click on this.
Click that one, for example.
And you click on See in Space, and you see this real magic happen.
Oh, wow. Oh, yes, we've shared quite a few of these videos whenever a new shower is detected. So it's really neat to see. So you get a visualization.
This is really what we are after. This is we are populating the solar system with these streams. We are now for the first time able to visualize how these meteoroids are moving. So somewhere in that distribution there is in the distribution of points is your parent body, is the object that let go of all this debris and that created this meteoroid stream. And each point you see here is not a computer simulation. This is not made up. This is actual data. Every point is one meteor we saw travel towards Earth's atmosphere, and we traced back to it moving in this orbit. And you can see that if you observe enough of the meteors that way, you can build up a really cool picture of how the stream looks like in space.
So we've come to our, we've been on for just over half an hour. I want to take a couple audience questions before we wrap up. Peter, approximately how many meteor showers are there each month?
So I think that it's hard to say. We have a list of over 800 meteor showers now that are being tracked, if you like, by the International Astronomical Union's Meteor Data Center, which is the organization that keeps track of the naming of the showers. And so potentially there are 800 meteor showers. Reality is that a lot of the showers proposed may not be real, because groupings of meteors that move in similar orbits were proposed as a stream, but then later proved to be just part of the sporadics. But who knows? This number could indeed grow into that sort of a level of showers, and that means that every month there is 100 meteor showers out there. If that's the case, then it means every night you're seeing a bunch of new showers, and that's what makes this field so interesting. We are really enriching the experience of going out at night and seeing these meteors, as well as getting a better understanding of what our Earth's environment looks like, what space around us looks like.
So with all of these various meteor showers and this vast amount of what is essentially cosmic dust surrounding us, one of the questions that's been asked that I'm kind of rephrasing is, how are we able to launch spacecraft and not be destroyed by all of this dust? Why does that work?
Yes, well, we have Whipple to thank for that. An astronomer who worked in the US on meteor showers a long time ago. In the 50s and 60s, when the first satellites were being launched, he came up with a really smart idea to take thin layers of aluminum foil. And if a meteoroid hits that aluminum foil, it breaks into pieces. And then those pieces hit the next layer of foil and they break into pieces, and so on. So it turns out that with a few thin layers of aluminum foil, you have a pretty good capability of stopping the small meteoroids. And those are the most, those hit the most often. So if a satellite goes into space and it comes back, you'll find it's dotted with little pockmarks everywhere, and that's from those micrometeoroids.
Okay.
Micrometeoroids.
Today I learned. So that explains why everything seems to be covered in layers of foil. I've always kind of wondered.
Yes. But if the particles are getting bigger, the ones that we are actually looking at, they're really not so well protected against, because these particles carry so much kinetic energy that they can penetrate those foils and can potentially cause problems. Now, the chance of being hit by one of these is really low, because they are so diluted in space. Space is so big. It made, in the planetarium program, it all looks great, but that's because we are plotting this meteoroid as a really big fuzzball, while in reality, it's just this tiny little speck. And so, chances of you being hit in space by something big is not that high. And so it's when there are meteoroid storms, when there are dense streams of dust, that satellite operators get nervous and want to know about it. And they have simple ways of dealing with the problem. For example, the biggest chance of being hit is when your solar panels are sort of facing the meteor stream. Then you have a chance that something hits the solar panels that can create electrons and ion plasma, and that can penetrate your electronics. And so you don't want to have that happen. So the simplest thing to solve that is by reorienting the solar panels so that there's the edge on. It's you know, relatively simple things like that that can you know, that can manage this problem usually.
Now, you mentioned that people can participate in this with just a camera or two, and we've been asked, are there any specific cameras that you would recommend to participate in the project?
Yes. We usually ask people to just contact us, and you know, if there is an interest to try and do this, contact us, because remember, CAMS is a triangulation system, so you need at least 2 people at the right sort of distance apart to start a network. You can't do this by yourself. And so so we usually say, okay, if somebody's really keen on setting up a network, contact us. We'll help you with setting up the software environment and so on, and get you started. And then you can build from there. So at the moment, we heard there was 1 person in Texas who is listening in, maybe more. People in Texas, be aware that a new network is being set up by Walt Cooney, and Don Sella has just set up a camera. So there's a bunch of cameras now being set up around Houston, just west of Houston. And if you're anywhere in that area, please join. You know, let us know you're living there. You want to do this, and you set up some cameras and contribute. And we have a very cool display on our website as well, where you can actually see who's participating in every given network and how many meteor to how many of the meteor trajectories your particular camera has contributed.
And
so
that can be found on
the results. Yes, you can see the results of your work and your contribution to this project.
And that can all be found on the cams.seti.org website?
And on the website Siddha is showing.
And on the Meteor Shower one.
Yeah.
Okay.
Yeah, you just click on the all locations over here.
Oh,
yeah,
okay.
we're just looking at everything, but you can actually also look at individual networks.
The names of people who have contributed.
And then you can see everybody who's contributing for a given network, and you will see it's big groups. It takes it takes many cameras to get lots of points on the map.
So, to that end, I'm gonna wrap this up, and I'm gonna point out one more time that we are crowdfunding for a student-run meteor observatory in India. The link is in the chat. We are doing that from Indiegogo. We only have a few days left on the official campaign, so please get your contributions in. We would love to see this built and operational and add to the data that Peter and Siddha are working on and processing, and it's all amazing. So thank you very much, Peter and Siddha, for coming and talking to us about the CAMS network and the project and the machine learning, all of it. It has been fascinating. And even though I've worked on it, I've learned a lot today, so I'm very excited. Cool. And as a reminder, next week, we do have our next SETI Talks event on Wednesday evening. Is oxygen really a biosignature? So if you want to come find out about that and why it might not be a good one to use, register for that on our Eventbrite, also linked on our Facebook page, and you can come watch that talk as well. Once again, thank you, Peter. Thank you, Siddha, for being here. Thank you, everybody, for watching. Take a moment to like, share, subscribe, throw bits at us, whatever support you can give. We always appreciate it. We like doing these outreach events, and we want to keep doing them. So your support is essential in that. And once again, thank you, everybody, and we'll see you next time.
Thank you so much.